Welcome everyone, and I must start by thanking you for staying uh, till 6 p.m. and we'll be spending next 1 hour to discuss this important topic, uh, electronics for sustainable future. And this is being organized as part of the 25th anniversary celebration of IEEE Sensor Council. As I mentioned yesterday, if you were present in the welcome presentation yesterday, the 25th anniversary theme is Sensors for Sustainable Future. And this aligns with the 25th anniversary theme. So today we have an outstanding panel, I must say, who have achieved, people who have achieved, researchers who have achieved a lot in the field, uh, connected to flexible and printed electronics, but also very much relevant to sustainability. So we have, I'll say from the left to right. So John is professor in Northwestern University. Unfortunately, he couldn't come today, but he's joining us online. He's connected with us. Welcome, John.
Hi.
So then next is Edger. He's Chief Technology Officer of E-Ink Incorporation. Welcome, Edger. Yeah. And then we have Professor Takao Somea. He's Vice President of the University of Tokyo, and he's President-elect of Material Research Society. Welcome. Then we have Ashik Ahmed from Pragmatic Semiconductor Limited, UK, and he's the sustainability lead at Pragmatic. And then we have Professor Gregory Abbott. He's Dean College of Engineering in Northeastern University. Welcome, Gregory. So looking at the field itself, if you look electronics, I can say that it's omnipresent. If you look at horizontal, vertical, in whatever way you see, electronics is very much part of our daily life. And so many things are if you look at the global challenges itself, without electronics, it would be very difficult for us to address the global challenges. But this electronics is also coming to us. We are starting to see problems in many ways, and some of the one example here is electronic waste. If you see some of the facts here, then you will understand the magnitude of the issue that we have. We are producing almost 60 billion worth of electronic waste every year, 50 million tons of electronic waste that we produce. And 80% of it, this is untreated. Only 20% goes to, is properly treated, and that rest goes to the landfill, then causing environmental challenges as well as health issues. And there is also significant loss of scarce material that is currently being that's also is a problem that also leads to problem in the supply chain, which we have been witnessing in recent years. And in terms of just one example here, we use a lot of gold in our fabrication processes. 7% of world's gold is contained in electronic waste, and that's, you can imagine, if you start with the mining, then purifying the gold, and then we eventually this ends up in the landfill. So such a waste. So what can be done in this direction? And this electronic waste is just end of life. During the process, the lifetime itself, as well as during manufacturing, that you can add that part also, how that contributes to unsustainability. So this is going to go up because our reliance on ICT gadgets is increasingly, it's growing rapidly. We have, people have multiple phones, multiple, iPads, etc. And that continues to grow. And with that, it is expected that electronic waste will also grow. So we have to look at solutions such as circularity. How can we extend the lifetime? How can we design the electronics in such a way that it can be used for a longer time? Can it be repaired? Can it be degraded and part of it can be reused, etc.? So it has to be a circular vision that we need to develop. And with that, the objective of this panel today, I have highlighted some of the points to develop a shared vision of the appearance of truly sustainable electronics. What should we do together to develop that vision, and how electronic hardware can be efficiently used to reduce the carbon footprint what can be done to extend the useful life of electronic products. This forum is also to discuss how end-of-life electronics can be reused into the front-end product design, discuss new materials and manufacturing methods, and to discuss the innovative technologies and new directions that will promote the sustainability, reduce electronic waste, and turn into new opportunities. That new opportunity could be new economic sector, for example. So also to understand, to discuss how environmental impact can be considered as a core element of future semiconductor industry. So currently that's somewhere takes the backseat. So we have to think about that. How can we bring it as a core element? And also this forum is to raise the awareness how sustainable technologies and sustainable engineering are being targeted by electronic industry today, and how they can change the practice so that we see more sustainability. With that, I will pass the to our panelists. We start with the order. First, panelists will have 5 minutes to share their views about sustainability, and I have some presentations here. So we'll start with from my left. We start with John, and then we move to Ajay. So it's the format. It says that we have one academic view and then we have one industry view. So that would be all right. John, over to you, please.
All right, thanks, Ravinder, for organizing this event and pulling together this panel to talk about this very important topic. I also want to apologize again for not being able to participate in person. I had a couple of travel conflicts that were impossible to resolve, and so please accept my apologies. So this is, very important topic. Obviously, we started thinking pretty deeply about this maybe 15 years ago, and I think maybe just to reframe some of the points that Ravinder just made in his introductory comments. So you think about the evolution of electronics. It's really focused on performance, cost, reliability, operational stability over time, and that's been a very powerful set of driving forces around the development of constituent materials, manufacturing approaches, circuit designs, and so on. But I think it's growing problem that's widely appreciated at this point, that there are negative consequences associated with those points of emphasis, in the sense that we're generating forms of electronics that are discarded on an increasingly rapid rate due to the development of new generations of devices, where the underlying hardware is designed to last forever, and so you end up with tremendous waste streams, solid waste streams of largely functional electronics that become problematic over time. And so, from a material science standpoint, I mean, that's kind of my core expertise. We began to think about how we might be able to contribute from the standpoint of academic research to alternative paths forward that might help to address these growing challenges in managing these toxic waste streams, solid waste streams. So if you go to the next slide, the vision really is to think about whether it's possible to build electronics out of water-soluble materials that can dissolve away harmlessly in a biological or an environmental scenario. And so the notion, I guess the vision is, a cell phone that would just melt away, under appropriate conditions, or, enzymatically degrade by bacterial action in a landfill to benign end products. And sort of crazy idea, and in some ways, and maybe you couldn't, achieve all of the functional components of something like a laptop computer. But even if you could make a dent in reducing the amount of solid waste streams, if you can't eliminate it entirely with this concept, that would be, a step in the right direction. And the other associated consequence of thinking about water-soluble materials is that the processing approaches and the associated wet chemical etching chemistries might be a lot more benign as well, because aggressive etchants wouldn't be needed. So this is a kind of vision for the future, maybe complement the more traditional evolution pathway for electronics. So if you go to the next slide, the way we got started in this actually was funding from DARPA and they were interested in developing classes of electronics that could be triggered to physically disappear. So kind of a physically transient form of electronics to avoid unwanted recovery of sensitive devices by an adversary. And so this idea of environmentally degradable electronics is sort of a subset of a broader class of technology that we're referring to as transient electronics, as defined, as systems that can fully or partly dissolve, resorb, or otherwise physically disappear at programmed rates or at triggered times. And the reason why I mention that is that, there's a collection of application opportunities here that can serve as a broader driving force, not just addressing challenges in sustainability, but opening up new classes of devices that have characteristics that are important and can complement those associated with traditional forms of integrated circuits. And so if you go to the next slide, it just sort of outlines what those applications might be. And just to kind of conclude my 5 minutes, so we just highlight number one is really most relevant to this panel topic. But the idea of temporary implants, and thinking about technologies that could serve as biomedical devices to enhance patient outcomes, or environmental monitors and sensors that could be distributed at scale, but wouldn't have to be recovered after they're no longer needed. And then the last two really focus on military systems and topics of interest to the Department of Defense. So I'll stop there. That's my 5 minutes, but happy to engage in the Q&A after these introductory statements have been completed.
Thank you very much, John. We move to Edger now.
It's better if I.
Yeah. Yeah. Go ahead.
So I was a little bit in doubt what to do. This morning I had the keynote. Number of the slides actually will come back here now again in order to introduce where we are, but also what to do on the sustainability front. I'm assuming that not everyone was here. I will go over it pretty quickly and then go to a last slide where I outline our more pragmatic approach to the problem. And it's actually great to see also from John that the radical approach that is looked at from the academia. I think it's a really good one. At this moment, as a commercial company, we're also taking kind of pragmatic steps, and I will outline a few of those in order to make good progress in the coming years. Very quickly, we are E-Ink here close by. Billerica was Cambridge, spin out of MIT, making electrophoretic material. It's kind of an alternative to LCD, to OLED, reflective, super low power. You can see that here. We make color materials, reflective color, front plane laminates, as we call it. You can attach them to any back plane and make a display out of it. Typically used for shelf edge, where you replace paper, or used for e-readers, where you replace an LCD or an OLED for reading, or make color changing surfaces. Quite a sizable company already, about 1 billion in revenue. If you now compare the three types of mainstream displays, and I discussed this morning as well, there's kind of a trade-off where on the right you see our electrophoretic panels, and in use they are orders of magnitude lower in power, and that's of course great also from a sustainability perspective. You only drive them when they're on, while all the other displays like OLEDs, LCDs need to be driven continuously in order to show content. And the other thing is actually more efficient. Even if you compare it to reflective LCD, you lose much less light, no polarizers, and you can make all colors in every pixel. So all of that adds to the benefit. E-readers, e-notes, main market, electronic shelf labels, another big market. And then looking at the use cases, it really is a very sustainable product already in use. And we see also that it becomes more and more attractive because of everything that's happening in society at this moment and the big emphasis on sustainability. An e-reader is already much more efficient than using LCD for reading, about 50 times more and even better than using paper because you cut down trees. Shelf edge labels even better. If you convert from paper to electrophoretic tag, it is 60,000 times better in terms of CO2 equivalent, and also much better than LCD. What I really want to, and the last one is actually on if you do signs outdoors and you power them by solar, of course you don't have any emission while you're using it, while an LCD still continuously uses the grid. Very quickly, and kind of a summary slide of how we approach things. It's actually as we discuss it internally, it's kind of a whole complex of different actions that you need to take. On the one hand side, you have the whole supply chain. So our big customers come to us as a supplier and tell us that we need to become more sustainable and have certain goals that they push upon us. We have a certain position in the supply chain. We have a lot of suppliers. And for instance, we are using backplanes, active matrices, ICs that we get supply from our suppliers. And we again start the same discussions with the same goals with our suppliers. So you see, starting, for instance, at Amazon as a big customer, this ripples through the whole supply chain, through us to our suppliers and down, where on the one hand side, you have a push for renewable energy. So our energy consumption needs to become renewable, although they'll never go to zero. Then the emission that we have within our organization needs to go down, but also outside our organization towards our suppliers needs to go down, and we enforce that. Also, that doesn't go to zero, but things like using thinner plastics, we are going from 4 mil, 100 micron, now to 50 micron plastics. It's kind of a big deal because in those substrates, in the glass, there's a lot of energy consumption. Speeding up the lines is a thing that just linearly helps in reducing carbon footprint of your things that you make. So there are a lot of those things that are really important. Another important thing is the embedded sustainability in our new technology introduction programs, but also in our product development programs. We have a whole, let's say, gated product development chain, starting from research right up to the point where we hand over to manufacturing. And in every step in that process, we now embedded sustainability as well. And we also train our engineers to be able to do a life cycle analysis together with dedicated people that we have now in our company that are trained, or actually they even have an education to do that. And we also have the databases and the tools to execute on those analysis with the aim to every time analyze how a previous product performed and then make steps to improve in the next generation. So that's the part of the design for sustainability. And then the last 2 points I already discussed: energy efficiency, supply chain engagement. So that's kind of the complex of things that we use to achieve the goals that we also get from our customers.
Thank you, Edson. So we might now move to our next panelist, Professor Takao Someya. To you, please.
So my name is Takao Someya, and I'd like to congratulate the 25th anniversary of Sensor Council, and also appreciate the kind invitation to this wonderful conference. So my research background is semiconductors, and obviously to realize the sustainable society, the first priority may be the reduction in power consumption for silicon chip. And now people are using the generative AI, and that requires the enormous amount of GPU and more computational power, and more power is needed. So we have to reduce the power consumption of silicon-based electronics. So this should be the most important task for electronics engineers. And I myself is working on large area printed stretchable organic electronics. And then I want to add the more comment from my own research viewpoint. The printing process is considered as the quite eco-friendly process with minimizing the material wastage. And also the process can be carried out at the ambient pressure. And we can reduce the process temperature as well as the we can reduce the we can minimize the use of high energy process to get the better performance. And also organic electronics can fully utilize the benefit of diversity of materials. And then the keyword could be self-assembly or recycling, and also biodegradability, as Professor Rogers mentioned. And also we are thinking about the application of such kind of flexible, stretchable electronics. And sustainability doesn't necessarily mean the response to the climate change. And particularly in case of Japan, we are facing the serious problem associated with the aging society. And aging ratio in Japan now exceeds the 28.4%. So, and then we are facing the problem associated with shortage of skillful workers. So I believe the automation and maybe getting more and more important, where the human interaction may play a very important role. Another problem associated with the aging is how we can monitor the health conditions that strongly depend on the individual. To realize the sustainable society, so we need to induce the mindset change of people. Thereby, the visualization is quite important. So in case of aging society, the elderly people have to take care of themselves with monitoring health condition by themselves. Thereby, the wearable tech is getting more and more important. And for long-term monitoring of health conditions, I believe the stretchable or soft electronics that harmonize the human may play a very important role. So I think the coming back to the original question, I believe the reduction in power consumption is the key, and also autonomization and also visualization of a health condition can be done by flexible printed electronics. So thank you very much.
Thank you, Takao. Now I would like to invite Ashik to share his thoughts.
Thank you, Prof. Dahiya, and thank you for inviting for the event. Good evening, everyone. So I'm Ashik. I work as a sustainability lead at Pragmatic, and here I'll give a very quick. Okay, I'll give a very quick introduction about Pragmatic and what we have done and how we plan to go further on the sustainability aspects within the business. So. Introducing Pragmatic. So we are a global leader in ultra low cost flexible electronics, and we are headquartered in Cambridge, UK, and we have a manufacturing facility at Durham, UK. The company was founded in 2010, so it's about 13 years old, and there are about 250 people, and we have almost doubled in the last 1 year after our Series C funding. So the company is growing very rapidly. And what do we make? So we make flexible integrated circuits. It's one of our primary products. It is more of a fit for purpose application. So we have managed to achieve it using alternative materials. We have reduced energy consumption when you compare to typical silicon ICs. And we have significantly reduced water, GHG consumption, and VOC usage. So basically, the IC chip production is 25 times faster when you take the cycle time, and it has a about 30 times smaller footprint, and it could be up to like 33 times lower production cost. And when you look at the entire life cycle of the Flex ICs or the product that we produce, so it has an inherent advantage. So basically, we use much less materials, and it is optimized for fit for purpose applications. So basically, it can replace conventional electronics within lower complexity applications, and it could also enable new applications where conventional electronics are unsuitable. And when you look at the typical silicon-based ICs, you hear all the news, right? So it has a huge footprint. So when you look at a smartphone, about 80% of your footprint comes from manufacturing, and of that 80%, over 50% is accounted by the ICs. So that's a huge footprint when you think about the life cycle of a smartphone. And one of the main reasons is it uses highly potent gases for silicon wafer manufacturing. So that has contributed significantly to the environmental footprint. So in our Flex ICs, we have managed to get rid of that, and we are using much more environmentally friendly gases in the production process. So when you break down the footprint of silicon IC, under scope 1, 2, 3 emissions. So scope 1 is direct emissions from the facility. Scope 2 is energy consumption, and scope 3 is everything else. So about 80% of the contribution is from scope 1 and 2 emissions. So which is huge and significant when you take the silicon ICs. So when we compare that with our Flex ICs, we were able to reduce it significantly. So our scope 1 and 2 emissions are much smaller than 20%. So scope 3 is more than 80% for us, and we are trying to reduce that going forward in future. So how we are planning to achieve that is, apart from the inherent advantage we have, we are also looking at improving our chemical and gases to safer chemicals and gases, and reduce the wastewater emissions and optimize the process. And we are planning to involve our suppliers to buy into this objective, and decentralizing production would help us to avoid the transportations involved. So that would again help us to minimize our scope 3 emissions. So yeah, thank you. I'm happy to discuss further during the discussion sessions. Thank you.
Thanks so much.
Yep.
And so I'm Gregory Aboud, Dean of the College of Engineering here. I'm actually a computer scientist, although my appointment here is in electrical and computer engineering. And I'm in an area called mobile and ubiquitous computing, and looking at human-centered applications of technology. And that's the perspective I come with. So I was very much early on in my academic career was influenced by the writings of Mark Weiser, an essay that if you haven't read, you should read. It's over 30 years old, but still incredibly relevant. About 10 years ago, 2 faculty members, I was at Georgia Tech before I came here to Northeastern, and people in material science and chemical engineering opened up my eyes about challenging some of the assumptions about how we make those things that are computation. They were looking at different ways of creating transistors without using highly integrated manufacturing techniques, and thinking about the low-level materials that go into the production of these kinds of objects. And this really inspired me. But initially, the inspiration was, what kinds of objects in the future could we imagine prototyping? This was around 2017 or so that might have some kind of future. So there are 2 quick examples I'll show you here. The first one is an example of a self-sustaining sensor, acoustic sensor, that when you speak,
Hello, hello,
will wirelessly transmit without any additional power and
hello, hello.
produce something that's like a wireless microphone with a thin, flexible, multi-layer material that requires no battery, simply uses a triboelectric nanogeneration effect and wireless RF backscatter to produce a wireless acoustic sensor. So you might think about this in the future as something that ultimately could become an electronic Post-it note. Be like paper, as cheap as paper, but have computational capabilities. Another example we looked at, and this is with a colleague of mine who's in the back there, Kenneth Fuentes, is how you might use patterns of light to understand human activity. And photodetectors, these weren't even particularly good photodetectors, are fairly low power requirements. So you could use existing solar harvesters to essentially create the ability to track walking or something that's on your wrist that doesn't need an external power source. And you might think of this in the future of being able to produce something that's like a silicone wristband, but is an activity tracker. But it costs and has the same form factor of silicone wristbands, but does things like the activity trackers today. So that's how I started down this path. But then very quickly realized that there's a much more serious reason why one should pursue this idea of creating these kinds of objects that are self-sustaining and are cheaper to manufacture. And it's largely because in today's world, we can see that we have an insatiable desire for creating more and more things that are computational and crunching more and more data in our data centers. Sustainability in the computer science field has really taken hold in high performance computing. It hasn't taken hold in what I'll call the Internet of Things world as much. We can't stop that desire to have more and more computation, but we can and must stop the way we produce things that are computational. And this is kind of the theme for today. And if you accept that argumentation, then we have to think differently about a number of parameters that we use to understand how we create things that are computational. We need to think more seriously about how they are powered, what materials we use, how the manufacturing processes we use, the life cycle implications from manufacture all the way to reuse, recycle, or disposal, and the measures of progress. And I think John Rogers said it best at the beginning. We think too much about the measures of progress being we can make things faster, cheaper, and more powerful, or can span longer distances. Those are not the only measures of progress that should matter. And so we need to break that mindset. So a lot of my, what I've been trying to do over the last few years is to get computer scientists to think differently about that things that they make that are computational. We usually think in terms of this kind of stack. We wonder, as a human-centered researcher, what are the problems of the world we're trying to address? And then we try to break that down all the way from applications to algorithms to systems that are made of circuits that are built from devices. But we have to go further than that. We need to think about the fabrication process that went into those devices that were made. And we need to think about the materials that are used, because we don't think about those things, we can't address a lot of the sustainability issues. And those two examples I showed you required knowledge and expertise at all of those levels. So what that means is if you want to play in this world that I call Internet of Materials or computational materials, you either need to work with a team of people that represent all of these perspectives, or what I think we really should be doing is training computer scientists to appreciate the importance of fabrication techniques, the manufacturing process, and the materials that they use, so that they don't start with things like an Arduino kit that already has inherent and not necessarily good sustainability properties. You can't affect sustainability if you start at that level. You can only affect sustainability if you go lower than that. So that's my little position statement.